Welcome back to Larry's Classroom. Today we're going to talk about multiplying and dividing fractions. Well, first we're going to start by talking about equivalent fractions. A fraction is basically a ratio. Let's say that you have two cities that you often go to. One of them you regularly go to shop, and it's 50 miles from your home. And there's another city that you travel to quite often, but that's on weekends. You like to go there because there's recreation you like there. And let's say that that's 300 miles from your home. Now we could say that from 50 miles you travel here, 50 to 300 is the ratio. 50 miles to city A, we'll call it city A, and 300 miles to city B. So the ratio of the distance to city A to the distance to city B is 50 to 300. Now you could reduce this fraction by dividing both of these numbers by 50. So this would be equal to 50 divided by 50 over 300 divided by 50. Now if we do these two divisions, we end up with 1 over 6. So what this tells us, when we travel to city A where we shop, and here is our weekend getaway, that for every 6 miles you drive to go to the getaway, you drive only 1 mile to get to the city where you shop. So it's a 1 to 6 ratio. 1 mile here for every 6 miles here. Now if we had the same fraction, 50 over 300, well, we'll leave that right here. Here, we'll take another fraction here. Let's say we had 100 over 600. And let's reduce that one. We'll do that by dividing 100 divided by 100, because we can divide both the numerator and the denominator by 100. In this one, we'll divide both the numerator and the denominator by 50. We'll do 600 divided by 100. We do the division, we end up with 1 over 6. So what we see here is that 50 over 300 is equivalent or equal to 100 over 600, which is equivalent or equal to 1 over 6. So equivalent fractions are fractions that can be reduced to the same number for lowest terms. Numerically, these all have the same value. They're equivalent, though they look quite different. We're going to talk a little bit about how you reduce a fraction to the lowest terms. We see that a fraction is a ratio, the number of units of the numerator to the number of units of the denominator. Let's take this one as an example. The fraction 16 over 28. We like to see fractions in lowest terms. That means that we have no common factors, no divisors that will both go into the numerator and into the denominator. Well, if you look at these, you can see that 16 and 28 are both going to be divisible by 4. So if we take 16 over 4, and 28 over 4. We do the multiplication. We have 16 divided by 4 is 4. We have 28 divided by 4, which is 7. So this fraction, 16 over 28, is equivalent to 4 over 7. But you might notice that there are no common divisors between 4 and 7. The only thing that goes into 7 is 1 and 7, neither of which will go into 4. 1 and 4 and 2 are what will go into 4, none of which will go into 7. So this fraction is what we call lowest terms. There are no common divisors between the numerator and the denominator, or some people might say the top and the bottom of the fraction. We're going to do another example here related to that same idea. We're going to simplify another fraction to the lowest terms. 28 divided by 70. Now in that last one, I'm going to put it back up here. 16 over 28. We said that was 16 divided by 4. 28 over 28 divided by 4, because 4 was a common divisor of 16 and 28, and that reduced to 4 over 7. So we found a common divisor and did the division. Another way to do that is factor each of these numbers into smallest possible factors. Well, 28 will factor into 2 times, and I'm just going to put these in parentheses because numbers in parentheses pushed up to each other like that, this is an implied multiplication. Implied multiplication. So we don't need to put any multiplication signs when we do it that way. If we take the denominator and do the same thing, we get a factor of 2, another factor of 5, and another factor of 7. Now we'll take a look at this. 2 times 2 is 4, times 7 is in fact 28. And 2 times 5 is 10, times 7 is in fact 28. And one thing you will notice about each of these factors, 2, 2, 7, and 5, we cannot find any numbers that will divide into them. They're the smallest possible factors. And we can reduce this 28 over 70 to smaller terms by factoring it completely, as we've done here. We've factored 28 completely, we've factored 70 completely, and then we can cancel like factors that are on the top and the bottom, on the numerator and the denominator. Well, here's a 2 and a 2. We can cross those both out and basically replacing them with a 1. Here's a 7 and a 7. We cross those both out and basically replacing them with a 1. All that's left is a 2 over 5. There's no common divisors for 2 and 5, so this reduces to 2 over 5. So we factored it completely. We canceled the common factors from the numerator and the denominator, and we replaced them with 1s. I'm going to write this slightly different. That's the same as going 1. That's where we canceled the 2 and made left a 1, times 2 times 1, because we replaced the 7 with a 1. We canceled. We did the same thing on the bottom. We canceled these two 2's, that left a 1. We canceled the 7's, which left a 1. And we canceled the 5, or nothing canceled with the 5 or the 2, so we have the 5 left. But we still have multiplication, and multiplying by 1 doesn't change anything, so we don't really need it. We can just get rid of that 1 and that 1, and that leaves us with a 2 over 5, the same thing we found in a couple of minutes ago. Now I'm going to look at this one little bit different way. Well, I'm going to wait till we go on the next step before I do that. But we're going to talk a little bit about prime numbers. What is a prime number? A prime number is a number that is only divisible by itself divisible by itself, and the number one. Well, every number is divisible by 1. 1 goes into 17 times. 1 goes into 1,000,003 times. 1 goes into 6 times. Every number is divisible by 1, and every number is divisible by itself. 17 divided by 17. 17 goes into 17 one time. 6,430,000 goes into 6,430,000 one time. So every number is divisible by itself, and every number is divisible by 1. Any number that is divisible by any numbers other than itself or 1 is not prime. For example, let's say 6. 6 is definitely divisible by 1. It's also divisible by 6, but it's also divisible by 2. That can be written as 2 times 3. So 6 is divisible by 2 and 3, so 6 is not prime. Let's take the number 24. Like all numbers, it's divisible by 1. 24 divided by 1 would be 24. It's divisible by itself. 24 divided by 24 would be 1. And all numbers are going to be able to do that. But 24 can also be, there are many ways to write 24. One way is 4 times 6. Now I'm going to note here that this is equivalent to 2 times 3. When I put them in parentheses like that and I push the parentheses together, there's an implied multiplication like we talked about before. And this is the same as, is equivalent to 4 times 6 in that form. Another way to write 24 would be 3 times 8. Sometimes we use a dot. Or 3, we'll use the parentheses form. But what we see here is that 24 is divisible by numbers. It's divisible by itself, it's divisible by 1, but it's also divisible by 4, it's divisible by 6, it's divisible by 3, it's divisible by 8, it's divisible by 2, it's divisible by 12. Obviously, 24 is not prime. 24 is not prime. Now, why we're talking about prime numbers, up here, 28, we broke it down to 2, 2, and 7, which each of those is prime. In 70, we broke it down to 2, 5, and 7. You don't see anything goes into 2 but 2 and 1. Nothing that goes into 7 but 7 and 1. Nothing that goes into 5 but 5 and 1. By breaking these down all into prime numbers, we call this a prime factorization. We know that we have no smaller numbers that we can break it down into, and we can fully simplify the fraction by canceling out any factor that appears both in the numerator and the denominator. So by factoring it to a prime factorization, as we've done here, and then canceling factors that occur in both the numerator and the denominator, we end up with a fully simplified fraction. It's in what we call lowest terms. There are no numbers that will divide into 2 and also will divide into 6 evenly. So there's no common divisors between 5 and 2, so we cannot reduce this fraction to lower terms. Talk a little bit more about prime numbers. We kind of talked about the value of doing a prime factorization, finding all the prime factors. That is, when we got a number factored into only primes, that means we have fully factored that number to. I'm going to list off some of the first primes. There are, in fact, an infinite number of primes. But we're going to list off a few of them. 2 is prime, 3 is prime, 5, 7, 11, 13, 17, and so on. When you notice about each of these, there are no numbers no divisors that go into 2 except 2 and 1. No numbers, no divisors that go into 3 except 3 and 1. 5 has no divisors other than 5 and 1. 7 has no divisors other than 7 and 1. 11 has no divisors other than 11 and 1. 13 has no divisors other than 13 and 1. And 17 has no divisors other than 17 and 1. And that's kind of the definition of prime. It has no divisors other than 1 and itself. There's a couple rules that can help us make it a little easier for us to do prime factorizations, to find common factors. When you want to take a fraction to lowest terms, you want to find the common divisors and cancel them out between the numerator and the denominator. So if a number is divisible by 2, you will notice, and I think probably most of you probably already noticed, the last digit is 0, 2, 4, 8, 6 and 8. So it's an even number. It's divisible by 2. And I think most of you probably can look at an even number and easily see by the last digit whether it's even or not. And what that tells you is divisible by 2. So if you're reducing a fraction and you have an even number in the numerator and an even number in the denominator, you know you have at least one factor of 2 in that numerator and in that denominator, which you can cancel out. So if you see an even number in the numerator and in the denominator, you know that fraction is not in lowest terms. And there's another one that probably everybody's pretty familiar with too. If a number, if divisible by 5, the last digit is going to be a 0 or a 5. So what can we tell here? Well, say you had 50 over 75. Because we have a 0, we know 50 is divisible by 5. Because we have a 5, we know 75 is divisible by 5. So we know we have at least one common factor of 5 in the numerator and 5 in the denominator. So we know this fraction is not in lowest terms. Now here's the one that probably isn't as commonly known. If the number, if divisible by 3, the digits add to a number divisible by 3. So let's list down here some of the numbers divisible by 3 that we can think of. Well, 3 is divisible by 3. 6 is divisible by 3. 9 is divisible by 3. 12, 15, 18, 21. So if we take a number, let's say the number is 3, let's see, 315, and we add the digits together, what do we get here? 3 plus 1 is 4, plus 5 is 3, plus 1, plus 5 equals 4, plus 5 equals 9. Well, 9 is divisible by 3, so 315 should be divisible by 3. Let's do the division, see if it works out for us. 315. 3 into 300 is 1. Subtract that. That leaves 15. 3 into 1 is 0. 3 into 15 is 5. So yeah, 105. And it's easy enough to see that 3 times 105 is going to be 315. So our test worked out. Let's try another one. 333. 3 plus 3 plus 3. That adds up to 9 again, which is divisible by 3. So we know 333 is divisible by 3, which 111, 3 would go into 333 at 111 times. Now the object of this is not to play tricks and divide by 3, but it's to give you some common factors that are easy to spot. It's easy to spot if a number has a factor of 2 because it's going to be an even number. It's easy to spot if a number has a factor of 5 because it's going to end in 0 or 5. A little bit harder, but not too tough to detect if a number is divisible by 3. Just add the digits up in your head, and if you get a result that's divisible by 3, you know that the number itself is divisible by 3. Let's take this one, 42. 4 plus 2 equals 6. That's divisible by 3. So 42 should be divisible by 3. So 4 into 42, or 3 into 42. 1, 30, 12, 14 times. 3 times 14 equals 42. So what we're doing here is looking at a few ways to quickly, fairly easily spot common factors, which will help us in recognizing that a fraction is not in its lowest terms. If we see that the top is an even number, or if the numerator, or if the denominator is, say, also an even number, we know it's not in lowest terms. If we recognize that the numerator digits add to a number divisible by 3, and the denominator digits add to a number divisible by 3, we know it's not an even number, or not reduced to lowest terms. So let's take one of these. Let's say that we have 24 over, well, let's go back to the 42. No, let's do something else. Let's do 36. Well, the sum of 2 plus 4 gives us 6, which is divisible by 3. 3 plus 6 gives us 9, which is divisible by 3. So we know both of these numbers are divisible by 3. So we know it can be reduced further. It's not in lowest terms. So if we divide the top and bottom, the numerator and the denominator by 3, well, 24 over 3, 36 over 3, that gives us 8 for the numerator and 12 for the denominator. Now we're no longer divisible by 3, but what do we notice? We still have even number in the numerator and denominator, so we know that these are both divisible by 2. So if we take 8 over 2 and 12 over 2, because every even number is divisible by 2, we end up with 4 over 6. Well, look there. We still have even numbers. So we know they're still divisible by 2. So let's do that one more time. 4 divided by 2 over 6 divided by 2 gives us 2 over 3. Now what have we got? Well, we have a prime number in the top and bottom. 2 is only divisible by 2, only divisible by 1. 3 is only divisible by 3 and only divisible by 1. So we have two different prime numbers. They cannot share a common divisor. So we know this is in lowest terms. So 2/3 is an equivalent fraction to 24 over 36. Now when we reduce a fraction to lowest terms, we are not always going to get prime numbers. What if this had been, let's see, let's pick a different one here. improper fractions. What if we come down to 4 over 7? What would give us an example? Give us 4 over 7. Let's see, what if we had, what if the fraction had been 12 over 21? All right, let's start with that one. 12 over 21. So these are not both even. 2 and 1, they're not even, so we know it's not divisible by 2. No zeros, no 5s, so we know they're not divisible by 5s. But if we add the 1 and 2 together, we get 1 plus 2 equals 3. And 2 plus 1 is 3. So we know the numerator and the denominator are both divisible by 3. So let's do that. 12 over 3 and 21 over 3. So what do we get here? We get 12 over 3 is 4. 21 over 3 is 7. Now, can we go any further? Well, 4 is even. It's got a factor of 2. But 7 is a prime number, so its only factors are 7 and 1, neither of which are factors of 4. So 7 has a divisor of 7, but 4 does not have a divisor of 7. They both have a divisor of 1, but that doesn't do any reducing. So this is in lowest terms, but you notice that the numerator is not a prime number. We don't always get a prime number over a prime number. As a matter of fact, we don't always get a prime number at all. But if we ever do get a prime number, either in the numerator or the denominator, we can't go no further. We're in lowest terms. So we looked at a couple little rules to help us spot common factors. This is not all inclusive. This is not the only way you're going to reduce a fraction, but it's some of the things that are easy to spot, and that's why we talk about them. 0 and 5 are divisible by 5. Even number 0, 2, 4, 6, 8 for the final digit, divisible by 2. Divisible by 3, the digits all add up to a number divisible by 3. And remember, prime numbers are only divisible by 1 and themselves. So we're going to talk about multiplying fractions. Well, we got a fraction, and these are variables, and variables are just containers for numbers. So A could be any real number, and B, same, any number. Suppose we want to multiply A over B times C over D. Well, how we do that is we simply multiply the numbers in the numerator by each numerator by the next numerator, and each denominator by the next denominator. So this is equal to A times C over B times D. So that's how we would do the multiplication. Now it can be helpful to put a fraction into lowest term before you multiply it. It is not absolutely a must, but it can. You end up working with smaller numbers, and it generally makes your work a little easier. Let's just say that we have a fraction 9 over 20. So ratio for every 20 you went in one direction, you might go 9 in the other, or every 20 pounds of flour, you might have 9 pounds of water, or whatever. You know, it's a ratio. We want to multiply that times 2 over 33. Now, we could just multiply these. We could just say 9 over 2, 20 over 33, 20 times 33, and we would get 18 over 660, I think it would be. And this is going to be equivalent, but it absolutely is not in lowest terms. We see even and even. But it's usually easier if you reduce these things to lowest terms before you start. So we can express the 9 over 2 as 3 times 3 over 2 times 2 times 5, and that fraction is going to be multiplied times 2 over 2 times 3 times 11. And you can see that 2 is simply 2, 3 times 11 is 33, 3 times 3 is 9, 2 times 2 is 4 times 5, that's 20. We can do like we were talking about before. Now we can just start eliminating factors that appear in both the numerator and the denominator. Oh, we've got a 3 here and there, we get rid of those. We've got a 2 here and there, we get rid of those. So now we just got a 3 in the numerator, and we have a 2, 5, and 11 in the denominator. So there's nothing left to reduce there. So we can say that's 3, 2, 5, and 11. Now we can multiply those out. The 3 on the top, 2 times 5 is 10 times 11. 10 times 11 is 110. So now we have multiplied 9 over 20 times 2 over 33 to get a number of 3 over 110. Now we know this is in lowest terms because 3 is prime. So there's not going to be any other factors that can be canceled. And, well, actually, if 110 was divisible by 3, then, so actually one prime number does not really indicate that you're in lowest terms. Because there could be, here's an example. Suppose I had 3 over 333. Now this could be expressed as 3 over 3 times 111. Now we have a prime on the top, not on the numerator, and a non-prime in the denominator, but 3 is a factor of this one. So the 3's could cancel. It would be 1 over 111. So basically, a prime number in the numerator or the denominator indicates it's prime unless, if the 3 is in the numerator and the denominator, or I should say, if prime is in, let's just go prime in numerator, and the denominator, unless the denominator is divisible by that prime, then it's in lowest. Unless the denominator is divisible by that prime, it cannot be reduced. It is not in lowest. It is in lowest terms. So what I'm saying is, if I have some fraction, x over y, and x is prime, then this is going to be lowest terms unless y is divisible directly by x. And the same token, if the prime is in the, if y was prime, if there was a prime number in the denominator, unless the numerator was divisible by that particular prime, it would be lowest terms also. So you can have, having a prime itself does not mean that it's in lowest terms. But if the prime is the numerator and the denominator is divisible by that prime, you can reduce it further. Otherwise, you cannot. If the prime is the denominator and the numerator can be divided by that prime, it can be reduced further. Otherwise, it cannot. In this case, we found that 3 is prime and 110 is not divisible by 3. 110 is not divisible by 3. So we know this is lowest terms. And there are a couple ways we can see that. One, 110 is even. Well, no even numbers are divisible by 3. Another thing we can do is add the digits up. Add the digits up. 1 plus 1 plus 1 plus 1 plus 0 equals 2, which is also not divisible by 3. So that's another way to show that 110 is not divisible by 3. The other way is just try to divide it out, and you'll see, let's see what we get. 3 into 110. It's going to go into there. 3, 9, 2, 0. 3 goes into 20. 6 times 18. Okay, so it's going to be 3.6666 repeating. But that is not going in an even number of times. It's not directly divisible. So we could divide 3 into 110. It's not directly divisible. That shows us that we can't reduce it further. We can also add the digits and see that they don't add to 3, so we know it's not divisible by 3. We can also see that it's even, so we know it's not divisible by 3. This is lowest terms. But the prime in the top and in the numerator and the denominator does not always mean that it is in lowest terms. Like we had 3 over 33. Well, 3 is prime, but 33, take a look, this is 3 for the numerator and 3 times 11 for the denominator, because 3 times 11 does in fact equal 33. Here we have a factor that we can cancel, replace it with a 1. We have 1 over 11. So these are equivalent. We had a prime, but it was not lowest terms. Now it's lowest terms. They're equivalent fractions. So multiply fractions, multiply all the numbers, all the factors in the numerator, multiply all the factors in the denominator. That gives you the numerator and the denominator of the resultant product of those two fractions. And product is a term we use for the result of a multiplication. So we're going to multiply a couple more fractions. 5 times 3 over 21 times 7 over 15. And remember, we need to multiply across the top, across the numerator, and across the denominator. But 5 is equal to 5 over 1. So we can do that for any fraction, any number, and make it in a fractional form. So 5 over 1 times 3 over 21 times 7 over 15. Now we can multiply across all the numbers in the numerator to get a new numerator. We can multiply across all the numbers in the denominator to get a new denominator. But it's worth our while to factor these into the lowest factors before we do this. Well, 5 over 1, that can't be reduced. 5 is prime. 3 can't be reduced, but 21 can be written as 3 times 7. So that one can be factored to the factors of 3 and 7. 3 times 7 is 21, so 3 and 7 are factors of 21. The 7 happens to be prime also, but 15 can be factored to 3 and 5. So we have factored these numerators and denominators in order to reduce everything to lowest terms to make the whole job a little easier. Well, being there are times, we could rewrite this fraction. That's what we're going to be doing anyway. 5, 3, 1, So what have we done here? We've just rewritten this very same fraction, 5 times 3 times 7, 1 times 3 times 7 times 3 times 5, which is exactly what we would do if we multiply this out. We can combine the fraction before we even do the multiplication, just by putting the factors both in the numerator and the denominator. They're going to appear there. And this makes it somewhat easy to see the cancelizations. Well, we got a 5 and a 5. We got a 3 and a 3. We got a 7 and a 7. What do we got left? We got, on the top, we just got 1 because we got rid of all these factors. There's always a factor. We always replace them with a factor of 1 when we cancel them out. We got a bunch of 1s top and bottom. Well, so what's the top? 1 times 1 times 1 is 1. That's the numerator. What's the denominator? 1 times 1 times 1 times 3 is 3. So lo and behold, this fraction, when we multiply this multiplication problem, we multiplied it out and simplified it, became 1/3. Now let's do this very same problem without doing any simplification. 5 over 1 times 3 over 21 times 7 over 15. If we just multiply all the numerators, we end up with 105. If we multiply all the denominators, we end up with 315. And one thing you might notice is 3 times 105 is equal to 315. So if we rewrite this 315 factored as 3 times 105, and then we cancel these like factors of 105, 105, we get back to 1 over 3. So what we've shown here is that 1/3 is an equivalent fraction to 105 over 315. And we get the same result either way. It wasn't arithmetically wrong, but we had a nicer setup once we canceled all the common factors. We got directly to 1/3. We didn't have to do the reduction afterwards. I want to show you one more thing with this problem. We rewrote the problem as 5 times 3 times 7, 5, 3, 7, over 1 times 3 times 7 times 3 times 5. Now we talked in the last lesson about multiplication being commutative. The order didn't matter. 5 times 3 is the same as or equal to 3 times 5. So we can change these orders, these multiplication, all we want to without changing the value. So let's see what we got here. Let's leave the top. Let's go 5, 3, 7. We'll leave that as they are, but let's change the order of the bottom. Let's move this 5 up front. 5. And let's move this 3 up. Well, yeah, move the 3's up there. One of them, doesn't matter which one. Let's move the 7 up front. Or up further to match the order. So we got a 5, 3, and 7. 5, 3, 7. We got a 3 and a 1 left to go. Let's put them in this order, 1 and 3. It doesn't really matter. But 1, 3, 7, 5, 3. 1, 3, 7, 5, 3. So we have 1, 7, 5, and 2 3's. Now let's match them up, get the same number of factors on the top and bottom. We can multiply by 1 as many times as we like to without changing the value. So now we got these lined up. Not that there's anything magic about this, but I'm trying to show you why this works. The 5's, the 3's, the 7's. So we can break this into individual fractions now. 5 over 5 times 3 over 3 times 7 over 7 times 1 over 1 times 1 over 3. So what happened? When we canceled these two 5s, we just got rid of a multiplication by 1. Multiplication by 1 changes no value, so it didn't change the value of the fraction. When we cancel these 3s, the same thing. We got rid of the multiplication by 1, because 3 over 3 is equal to 1. Same thing with the 7s. The same thing with the 1s. And all that was left was the 1 over 3, or the 1/3. So when you're canceling factors between the numerator and the denominator to reduce a fraction to lower terms, what you're really doing is just throwing away multiplications by 1, which is never going to hurt your value any. Multiplication by 1 doesn't change anything. Let's talk about division of fractions now. Division of fractions is very similar. A over B divided by C over D. This is equal to A over B times D over C. You've probably heard that said to divide fractions, invert and multiply. What we've done is taken the second fraction, which we call the divisor, and we've inverted it to get the reciprocal, C over D, D over C. These are reciprocals. Reciprocals. So we can divide by multiplying by the reciprocal. We changed our divide to multiply, and we changed our divisor to its reciprocal. Now it's just a multiplication problem. So that's the way the basic rule for dividing fractions, and you've probably heard this said, invert and multiply. We're converting the divisor into its reciprocal, and we can also rewrite this as an equal sign here. To multiply now, we multiply across the numerators, we multiply across the denominators, making it just a single fraction, A over D times B times A times D times over B over times C. And sometimes with variables we just push the variables together and do an implied multiply. Don't have to write the multiply sign. So AD over BC. So what we've found out is this division problem is the same as this result. It's the same as this result. It's the same as this multiplication problem. So we're going to do an example of actually dividing a fractional number. See how that comes out for us. Here's our example. 5 over 24 divided by 15 over 16. First step, we want to convert this division to a multiplication problem because we know how to multiply problems. Well, the first fraction stays the same, 5 over 24. Now we want to change this to multiply, and the way we do that is by converting this divisor to its reciprocal, 16 over 5. So now we've converted it from a division problem to a multiplication problem. We like to get to lowest terms to make things simpler. So well, 5 can't be factored. 5's prime, it's only divisible by 1 in itself. 24, well, what do we got? 2 times 2 times 2 times 3. I think, let's see how this comes out. 2 times 2, 4 times 2 is 8 times 3. Yeah, so 2 times 2 times 2 times 3 is the same as 24, equal to 24. Let's see what we do with this one. 16 is 2 times 2 times 2 times 2. A lot of 2's in this problem, huh? So, Now we can start canceling factors and replace them with 1. 1, 1. We have 3 2's we can replace. 3 2's. All 1, 1, 1. What's left? We have for our numerator, what's left, we have a 2. And for our denominator, 1. So this whole thing becomes, somehow I think I got it backwards here. No? Okay, here we go. We have a 2 and we have a 3 left here. So we have 2 over 3. That's what's left. I've missed that guy. After we canceled all this, 2 over 3. So this whole thing reduces to 2/3. No, I didn't do that right here. I missed this. This is 15. Okay, so I messed it up yet. So this was, okay. When I inverted my divisor to get the reciprocal, I dropped the 1, so this was 3, 3, and 5. We canceled these 2's. And we canceled these 2's, we canceled the 5's. What's left was 2 for the numerator and 3 times 3 for the denominators. 2. That give us 2/9, which is in lowest terms because there's no common divisors between 2 and 9. So this thing, we replaced the divisor with its reciprocal, turned it into a multiplication problem, then we factored to simplify, put things in lowest terms, which made it pretty easy to make the 2/9 result. We could have done the 5 times 16, which would that be 5 times 50 and 30, that would be 80, right? Over 240, I think it'd be 80 over 360. Does that sound right? 40 would go into there. If I divide both by 40, that would be 2 and 4 into here. Yeah, I think that would be 9. 9 times 4, yeah. Same equivalent fraction, but more complicated to work with. By simplifying it before we did that, that made the final result a little easier to obtain. Couple more here. 2 divided by 6 over 15 times 1 over 5. Well, we want to convert this to a multiplication, right? Because we divide fractions by inverting the divisor and multiplying. So what do we do? The 2 we're going to make 2 over 1 because 2 is equal to 2 over 1, and then we can do that with 8 because we want these all to be fractions because we want to multiply the numerators, multiply the denominators when we're done. And we're going to multiply it times 15 over 6 this time. We got the reciprocal of 6, and that doesn't change, times 1 over 15. 1 over 5. So now we've converted it all into multiply. We can multiply all the numerator factors, multiply all the denominator factors, but it's a good idea to simplify them first. Well, 2 doesn't simplify, nor does 1, but 15 simplifies to 3 and 5, 6 to 2 and 3, 2 times 3, and 1 doesn't simplify, and 5 doesn't simplify because it's prime. But now we can start canceling factors. We got a 2 here, a 2 here. We got a 5 here, we got a 5 here. What's left? We have just 3 and 1 on the top, 3 and 1 on the top, the numerator, and we have 1 and 3 left on the denominator. Well, pretty cool here. The 3's cancel, the 1's cancel, these 1 and 1. So this reduces to just simply 1. Interesting how that big fancy thing here was equal to 1. But you see how reducing the fraction made that quite easy compared to going, what we have, 2 times 15 would have been 2 times 15 would have been 30 over, well, that ain't too hard either. It multiplies over 30. So it's pretty easy to see 1. But if this had been something other than 1, it wouldn't be necessarily as easy to see. But you can see how it's advantageous to factor. It is not a mathematical requirement, but a lot of times it will save you a lot of work when multiplying or dividing fractions to put your fractions into lowest terms. We've got one more one to look at here. Okay, so we're going to calculate out, we're given this as a fraction. 5, 14 over 7 times 15, 6. Now we can multiply those out and and then simplify it. Another way, we can notice that this is equal to, we can divide these up 5/7, that's this piece, times 14/15, that's this piece, times 1/6. By putting a 1 in there, we can always add a factor of 1, don't change the value. Well, 5 can't be factored, nor can 7. Those are both prime, divisible only by 1 in the cells. 14 can be factored to 2 times 7, and 15 can be factored to 3 times 5. And 1 can't be factored. 6 can be factored to 2 times 3. So now we got these fully factored. Actually, everything in these lists are prime numbers, so we know we can't reduce it any less, so we can cancel factors 5 and 5. And we can replace them with 1. The 2 and the 2 can cancel, we replace them with 1. The 7 and the 7 can be factored, replace them with 1. So what have we got left? We got, on the top we have 1 times 1 times 1 times 1. And on the, that's the numerator. On the denominator we have 1 times 1 times 1 times 3 times 3. We can throw away all these 1s except one of them. We cancel 3, we need 1 to, we got to have at least a 1 in the numerator. What's that leave us? 1 times 3 times 3, 1/9. So this funny thing we started out with here, which was 5 times 14 over 7 times 15 times 6 was equal to 1/9. And we did that by factoring these further and canceling the common factors from the numerator to denominator, which made it easier to work with, not a lot left. So we've learned about multiplying and dividing fractions. We've learned about the value of reducing fractions to lowest terms. We've talked a little bit about what a prime number is. And we've looked at some quick little rules on how to determine if a number is divisible by 2, which we found if it is 0, 2, 6, 8. It's divisible by 2. If it's divisible by 5, it ends in 0 or 5. And if it's divisible by 3, the digits of the number add to a number divisible by 3. And those were just aids to help us quickly see possible ways to reduce a fraction. Anyway, I think that's enough for today. Thanks for coming back. Remember to like and subscribe. Until the next time, keep on learning.